Well, hello again. Last possibility for question with those sheets of paper. So I'm going to turn for the new pile of papers. I start with a new topic, which is optimization. Now my lecture on optimization will be more optimizer user oriented, and will be broken into two parts. Today I will talk about classic optimization, statement of the problem, classic methods. Let's say this is a little bit old topic. It's something like 1990. Then there has been plenty of new methods, mostly inspired by the nature, like ant colony, particle swarm, and other methods. And that would be something I would cover in the next lecture with you. Anyway, this is quite important. Some of you had some knowledge in the entrance test that resulted from your mathematical education. It seemed to me that that was quite oriented on methods that are not very used in reality, but I will try to show a few methods or a few approaches that are really used by the authors of software that you can buy, like circuit simulators or field simulators and so on. So first point, what the optimization for an engineer, for a designer means mostly, and automated optimization in fact. It means that you have some design goals. And those design goals should be met by the design. So those goals, let's mark them GI. In order to get this into classic optimization, we would be forced to have some numerical, some exact equations, some exact way how to find out whether the goal has been met or not, and how far are we from the goal. Now, in most of the optimizations problems, we do not have just one goal. That would be rather easy. So we have a set of goals. For example, if you design an amplifier, you would require that the amplifier has some gain, otherwise you would not need it. But besides the gain, you would possibly require that it's stable. So you would require some value of a stability factor. And with a radio frequency or microwave amplifier, you would also request some conditions on the return loss, on the reflections from the input and output. So you would have a number of goals. At the same point, you might have some requirements on frequency band. So you would have a set of goals, not just one goal. And unfortunately, like in real life, many of those goals are contradictory. For example, to have a well-stabilized amplifier, the best stability is achieved when there is no amplification. There might be no oscillation at all. Unfortunately, this is not why you build amplifiers. So some of the goals may be contradictory. The second point that is important is to understand a term which is called criterion or error function. Error function Well, now error function is a way how to grade or mark all possible solutions and distinguish better from bad solutions. So an error function is a prescription that gives to any solution a number. There is a number of ways how to construct an error function. In classical optimization, it's mostly done by the definition how much the result differs from the ideal one. So, in fact, for example, if we have goals GI and real performances of a circuit PI, then we could, for example, create something which is similar to the Euclidean norm, so the distance in our three-dimensional space, and that would be done most simply like a function which is mostly called least squares, and that would be a sum over all goals, and what we will sum would be GI minus PI, that is the goal minus real performance, the difference, squared. And after summing all those squares, we would perform a square root. Just remember, this is the way we calculate distance in our Euclidean space, in our 3D space. Just we have only 3 dimensions, x, y, and z. So this function is called least squares, and we should understand this bracket adequately. For example, if I require the amplification at least 12, then if I have the amplification, the gain 20, I just set this to 0 because it's satisfied. So this is we have to evaluate it wisely. But if I have the gain only 10, then there is some error, some difference from my ideal performance, and I count it. Now, I have omitted some space here, and I will tell you later why. This is not the only possible formulation. This is a good formulation that gives you a good result on average. Well, but there are some cases when average is not a good formulation of the task. For example, if you wanted to design a chain, it is not important, not a little bit, what is the average strength of one part, because the chain would break according to its weakest part, and then it's lost. So in that case, an average like this is not a good idea. In that case, we would like to optimize so that we minimize the maximum deviation. So the other possibility, which is mostly called minimization of maximum difference, or abbreviated minimax, would be the maximum over all goals and performances, and the maximum would be taken from the absolute value of GI minus PI. Other values are not important, only the maximum deviation, like in the case of optimizing a chain to be able to bear maximum load. So those are the two main formulations of an error function. An error function assigns a number of imperfectness to any solution, and giving this function you specify how to find the optimum. In an ideal case, a situation where you can meet all your goals simultaneously. In some cases this is impossible, and then it takes some difference or gets you to an optimum, which is fulfilling most of the goals. Now, in the case that you have not the possibility to meet all goals at the same time, it is very important to consider another topic. For example, if you want to find out, let's say, an equivalent circuit of a transistor, well, let's say if you have a high frequency field effect transistor, it could look like you would have an input capacitor with its field effect transistor. The voltage on this capacitor drives a current source, and there is also an output capacitor. This is a lossless model, idealized, the simplest model that would somehow describe a microwave transistor at low frequencies. Now this model lacks one important point. The transistor mostly exhibits also something which is called a Miller capacity since the time of electron tubes, and this creates a feedback from the output to the input, and it characterizes at the point the instability. So if you omit this feedback, you would get a miraculous transistor. Now, classically, this feedback is responsible for backward transmission through the transistor. So if you have the transistor, you get some transmission of the signal from the output to the input through this. And classically, it's very small at low frequencies, several order of magnitude smaller. But it's important. Now, if you have measured some data, they always have error. So you can never really stitch it to the model. So even if I got real two capacitors and an ideal current source controlled by the voltage, and I measured the results of this circuit, not of a transistor, but of this ideal circuit, due to measurement errors, I could never get zero over here because there are some discrepancies in the data. And at this moment, if there is something which is very small, like the backward transmission through that Miller capacity, the optimizer would not find it unless I somehow stress it is important. And that's why all those functions have one more important point, and that's a weight. So each goal has a weight. Some of them are more important. Classically, if you do not specify anything, the weight is set to 1 for all goals. But in most of the optimizers, you can somehow stress the goal by setting higher weight to that single goal or quantity. And of course, if you stress a negative weight, you do just the opposite. So if you stress, I want the transmission to be more than 20 dB and the weight is -10, in fact, you say I want it less than 20 dB. So any of the functions has also a weighting factor W, for example. With this, you have learned about the error function enough. Just there is a number of other formulations of error functions that is very proper for some cases. But those are the two most important. There is one point you should understand about error functions that is not straightforward at the beginning. It seems somehow that the main property of the function is that it becomes zero if all conditions are met. Yes, this is true, but it's not important at all. Because once you have met all conditions, you do not need the error function anymore. You have achieved the result. It's much more important how the function behaves around the optimum. And that's a bit tricky because we mostly optimize a function of several variables, 10, 20, in some field simulations that might be 100 of variables, like different dimensions of the circuit. And in that case, the error function is, could be displayed in multi-dimensional space, but still it's difficult to understand it. I would like to show you one problematic thing. I will borrow that from a simple circuit and show you why the formulation of the error function is important and the optimization isn't as easy as you might think. And this simple circuit is a resonating circuit, LC resonator. Well, let's say that we have an antenna and we have a receiver, and unfortunately there is a strong transmitter of working fortunately on another frequency, but it's quite near. For example, you have a radio amateur who has a 20-watt transponder and you try to receive a weak signal. Although the frequency is different, 20 watts neighborhood creates a strong field that could make it through your input circuits into your receiver and then cause intermodulation, and that's the end of the game. So anyway, you would need to beat that signal somehow. You would need to add additional selectivity. So what you can, for example, do is that you have a circuit that is a parallel resonance circuit, and before the signal gets to the receiver, you have the resonance circuit that is tuned so that it oscillates or resonates on your required frequency. So in fact, a parallel resonance circuit is not in the circuit. The impedance of a good parallel resonance circuit in resonance is reaching infinity. So this, all the signal goes to the receiver. At other frequencies, at lower frequencies, the signal is shunted by the inductor. At higher frequencies, the signal is shunted by the capacitor. So it damps all other frequencies significantly. Now, you would wish to design the circuit. First, although we have drawn it with this ideal case, it's not the true. The receiver has some input impedance. If it has a capacitive part, it adds to the capacity. If it has an inductive part, it adds to the inductor. But anyway, it has some real parts, so we have to include a resistor here. let's say that it's 50 ohm or 75 ohm or any receiver input impedance that is normally even printed on the box of the receiver. And now we can start to analyze the case. So first, without this resistor, we know that the resonance frequency of such a circuit is given by the Thomson's formula, which the resonance frequency would be 1 over 2 pi and a square root of the product LC. And this becomes, by the way, a little bit difficult on the thing, because if you simply decide to design the circuit, you have two variables, L and C, and they work against each other. If you increase inductance, you should decrease capacitance, and vice versa. But it's quite interesting if you have your goal, and our goals should possibly be, we have the frequency, we have the transmission, let's say, and we want it to pass some signal. So our goal would be over here, we want, let's say, let the transmission at the correct frequency is over 0.97. So not much energy is wasted in this circuit, and we would design some stop band frequencies over here and here. Let's say 20% of the frequency to left, 20% to the right, and we would need a transmission under 0.01. That's a nice description. Well, if I told 20%, it would be possibly better to do it just under 0.1, because otherwise it would not be technically sound. So